Okay, so a very good evening, everyone, and thank you for joining today for this week's live session. In this week, Professor Ajit Kumar taught us about for loops, while loops. He also mentioned at the end of the second video lecture something called as star args and star star KW args. After that, we discussed about creating modules. So module is, if you recall, it's basically a library of functions. So more than one functions being placed in the same Python file, and that file, through that file, we import those functions. About half of the week, second half of the week, we spent on understanding and using NumPy, like what all different functions there exist in NumPy, how do we use it, as well as matplotlib. Matplotlib, if you recall, is a library for plotting graphs, which can either be static or or animated as well. With this in mind, I have tried to cover I have tried to cover the key concepts taught in this week's lectures, as well as some of the open questions that we might have after the video lectures. So we'll go through the first example. Yeah. So in the first example, I wanted to showcase what star args and what double star star KW args is. Professor mentioned something called as star args and double star KW args. So what are these and how do we use them? This was discussed, I think, at the end of the second lecture when we were studying the while loop. So star args basically allows you to pass variable number of positional arguments to a function. So what does this mean? So far, functions that we have seen, they basically take say one or two or four or five different arguments and say like this Fibonacci function, and this takes like a single argument. There can be functions which will take more than one argument. But what would you do in the case where you do not know a priori how many arguments this function will take? So that is where star args comes to our rescue, wherein it will collect all the parameters and place them into a tuple, and that tuple is then used to perform some sort of operation. So an example of the same is this function that I have written, which is called as sum all, which uses the star args as the argument placeholder. And what I am saying is that for each number in this args, we are summing it up to the total, which was initialized to 0 at the beginning. And then we want to return the total. So if I run this function and say look at the first example, in the first example, you can see that the sum all function has say 5 arguments, 1, 2, 3, 4, 5. And if I run and print the result, you can see that the sum is 15 as expected. We can also run a different example wherein we have, say, only 3 arguments. Now, what would happen in the case, suppose if I were to play around with this and add a different uh, different type data, which is character, which is the string A. You could see that as expected, this an integer cannot be summed up with a string. So while we can pass any number of different arguments based on the function definition, we have to be careful what those arguments turn out to be. Another function could be simply a product function of all the arguments involved. So an example of the same. So, I think this is better. So an example of the same is basically a product of the numbers 2, 3, 4, 5, so on. So if I run this, we can expect 2 into 3 into 4 into 5, which is 6, 4, 24, 5, 120. Similarly, different a different number of arguments being passed into the product function. next is the double star KWRs, which refers to keyword arguments. This basically allows you to again pass a variable number of keyword arguments, but it instead of collecting into a tuple, which was the case with star args, double star KWRs basically collects all these arguments into a dictionary. Sure. Okay. Uh, and it's important to note that this args can be, say, I can rewrite, say, something like a. But if I place the star here, the function should remain unchanged in its characteristics. So as you can see, the function remains unchanged. If I suppose change this to, say, BBB, and then take the rerun the product function, again it remains fine. This star is the star is the important part. This is what informs Python that uh, you have a variable number of arguments. Similarly, you have two stars for keyword arguments, which becomes a dictionary. In the last class, we had looked at the different methods which are associated with a dictionary. One of those was items. If I have to, if you can recall, items contains both the key as well as the value of the dictionary. So, like a corresponding, uh, a, like a a list of key comma value tuples, and those are now being called in this function. So suppose I am passing my input as a dictionary called as info, which has keys, name, age, and city with some values to it. And if I run this print info function should print a key, then a colon, and then the corresponding value, which is what we are seeing here. Okay, another example of the same. So instead of 3 arguments, I have 4 arguments being passed, 4 keyword arguments being passed as a dictionary. So this is how star args and the multiple arguments and multiple keyword arguments can be used in Python. Okay, another remark professor mentioned in passing was that we could create a model in, say, a different directory. Suppose you are running a project where you have to create separate modules for different parts of the project, and at the end you want to import some specific function from a different directory from a particular module. So how do we do that? As an example, I'm gonna look at the Monte Carlo function, which tries to approximate pi, and place that function in a Python script which is outside our current working directory. So as you can see, my current working directory is something called as 2024 NPTEL SageMath, followed by live session material. So this is my current working directory. I'll go to a different directory where I have already done this. So this is my Monte Carlo pi function. Again, a straightforward function. We have seen this example, I think, 4 or 5 times in the class already, but how it does the estimation is, it will take n number of samples and assign an x between 0 and 1 randomly, assign y coordinate again between 0 and 1 randomly, and check if this random point x comma y first lies within the first quadrant of the unit circle, and if it is so, we know that the ratio of samples inside the boundary of the circle to those outside will be pi by 4. So we just calculate the ratio and multiply it by 4. You can see that this is a different directory, and now I'll go back to my home directory, which is live session material, and we are back to our current our current Python notebook. So I'll use something called as the OS module and use that to print the full path to our current working directory. So you can see that this is where I am, 2024 NPTEL SageMath live session material. And then I'll use this system module to basically uh, append what or rather to add a different directory along with my current working directory when I'm running this code. So I'm placing the directory name which we just saw as 2024 NPTEL SageMath class notebooks. This is being placed using. This is being added to our current path using the system module. That basically tells Python that this new directory is also part of my current working directory and I will use that going forward. Once that is done, I'll from the Monte Carlo Pi file, I import the function estimate pi and then just give a number of samples for it to try and calculate the value of pi. If I just change this again. So you could do a similar thing. Suppose you are running a project which has multiple subdirectories involved and you want a specific function from a specific file but do not necessarily want to import all the files associated with it, then you could use the system path append command to add the module directory along with your current working directory. Okay, so are the first couple of examples clear? Like both the args, KW args, and this importing module. Does anyone have any doubts here? Okay. If at any time you have any doubts, just either raise your hand or you can even write it in the, I think, chat box. Yeah, we do have a chat box here, so you could post it on the chat box as well. Okay. Next example that I have is basically one of similar to one of the practice examples given for given for exploration. So we want to write a Python code to calculate the Fibonacci series Fn for a given number n. So the entire Fibonacci series, and once that is done, we want to calculate the ratio of Fn plus 1 and Fn and see how what happens to it. So it's a well-known result that uh, this ratio of Fn plus 1 to Fn, which is the n plus 1 term of Fibonacci series to the nth term of the Fibonacci series, converges to golden ratio. If you want to see, what golden ratio is, you could actually there is in SciPy there SciPy constants dot golden ratio. So I believe SciPy is in the upcoming week's lecture, SciPy module. So within SciPy module, you have a bunch of constants that are used a lot, and one of those being the golden ratio. Okay, so we expect this ratio to converge to this golden ratio value of 1.618. And we first begin by defining our Fibonacci sequence with n terms. So okay, our, our first two terms are 1 and 1, and sorry, and we want to see uh, what we are seeing is basically run a while loop by checking. So If you remember, in the while loop, there is a condition that has to be satisfied for the loop to be running. That condition we have set to mimic, to ensure that our length remains less or equal to n. The moment it becomes the moment it exceeds n, we sorry, will be exiting this while loop. And the next term in the Fibonacci sequence is basically the sum of the previous two terms of the Fibonacci sequence. So this is the last term, Fib sequence minus 1, and this is the second last term, Fib sequence minus 2. They are being summed to obtain the n plus 1 net term, and then we add this term using the append command to the original list. And this should help us return the Fibonacci sequence. So when I run this, you can see that in the Fibonacci series, we expect the first, suppose I run the first 10 terms, then you can see that they are all sum of the previous two terms. So 1, 1, then 1 plus 2 gives 3, 2 plus 3 gives 5, 3, 5 gives 8, and so on. Alright. Next, we use this sequence function to calculate the ratio of fn plus 1 to fn. And the way we do this is we call we could we could call the Fibonacci sequence twice, once for n plus 1 or once for n, but that would be redundant because the n plus 1 Fibonacci series will contain like all the series from 1 to n. So we just call it once. Then we look at the last term. So this is our n plus 1 net term. And we look at the nth term, which is the second last term. And ask this function, Fibonacci ratio function, to return the ratio of the last term to second last term. And now I'm just doing this. Now I'm just printing the entire ratios of Fibonacci series, and you can see that with steps of 2, so f2 by f1, f4 by f3, f6 by f5, and so on. You can see that by f12, around f12, f11 point, this is starting to look like the first three digits are converged to what we expect of our golden ratio. And if we keep on just running this series, you can see that this will eventually converge after, I think, about this point. After this point, it almost converges to the golden ratio itself. So, okay. Okay, this example is hopefully this example is clear. Uh, any doubts here? Or otherwise, I will move forward to the next one. Okay. Uh, we are now solving this example where we want to write a Python program which will generate n points p1 to pn, which are equally spaced on a unit circle. So the radius is equal to 1 of this circle, and it is centered at origin 0, 0. Then we are asked to create a polygon from these points and find its perimeter. And finally comment on what happens to the perimeter as n increases. So the first step, as in any code, is that we'll import the relevant modules, which are matplotlib, pyplot, and numpy. Next, we will split this problem into different steps. The first step being we want to generate the points p1 to pn. The way to do so is using this equally spaced points on a circle function, which takes an input n. So the input argument is only one value n. So what does this function do? It first divides the circle. So the circle has a total angle of 360 degrees or 2 pi radians, and it divides this entire angle into n equal parts. So 2 pi by n. This becomes my angular step or delta theta. Next, this step is used. This angular step delta theta is used to calculate the x and y coordinates of points P1 to Pn. So how do we do this? The logic for the same can be seen through this notebook, can be seen in this notebook. So as I mentioned, our delta theta is constant here between any two consecutive points Pn plus 1 and Pn, and any point xi comma yi which is associated with the point Pi can be written as r cos theta and r sin theta. In our case, r equals 1 and theta equals I times delta theta. So xi becomes cos of I times 2 pi by n, and yi becomes sin of I times 2 pi by n. So this is basically our point Pi for our problem, and x and y coordinates, to quickly recap, simply come from the polar coordinate equation. Okay, uh, right. So with this in mind, we looked at the different sides. P1, we looked at what the points are in our function. So the points are, I'll go back to the notebook once again. My points x and y coordinate being cos of delta theta, I times delta theta, cos of angle and sine of angle, with angle being I times step of angle, I times delta theta. If we say only have 4 points, we expect them to be on the 4 axis, like positive x-axis, positive y-axis, negative x-axis, and negative y-axis. Then we looked at the polygon perimeter function, which is as follows. So again, I'll go back to the notebook quickly. You can see here that the sides, as I mentioned, are P1, P2, P1, P2, P2, P3, Pn minus 1, Pn, and the last side is basically this P4 to P1. So again, you go back from Pn to P1, and the length of a side is nothing but the distance between the two endpoints of the side, which are Pi being xi and Pi plus 1 being xi plus 1 yi plus 1. From this, you calculate the distance di comma I plus 1, which is the length of this side, and then we send it back to our code. So our code is so okay. So in our code we have this function called as polygon perimeter, and it takes input as something called as points, only one argument. We initialize our perimeter to be 0, and to that perimeter variable will be adding one by one all the lengths of all the sides. So this function is generic in the sense that this would work uh, even for points which are not equally spaced. So that is how I've written this code. We initialize n to be the total number of points that we have for our problem. We run a for loop. So the for loop will go, total we have n points, but we are running the for loop only till n minus 1 points. This is because in the for loop we are calculating the first point as Pi and the next point as Pi plus 1. Pn being the last point, our maximum value of I will be restricted to n minus 1. We calculate pi coordinate, we calculate pi plus 1 coordinates, then we calculate the distance between those 2 points, which is the length of the side, and add this side length to our variable perimeter. At the end of our for loop, the one final side is remaining, which is pn comma p1. So we wrote this function with an else conditional at the end of this for loop, wherein we assign the last point and the first points as the two ends of our side, and from that calculate distance and add that again to our perimeter variable. Overall, our function returns perimeter. If you recall, this else conditional will only be triggered when all the possible I values are cycled through by our for loop. So now I run this function polygon perimeter, and suppose I only have a four-sided polygon, which is, as we saw in the notes earlier also, which is basically a square rotated 45 degrees. I'll ask it to uh, I'll ask it to print. So what are we doing? We are calculating all the points, and we are telling this cell that if we have less number of points, say up to 9 points, print points. Otherwise, the list will be too big to print anyways. So that will jumble up some of our understanding. And then we are calculating perimeter using the polygon perimeter function with input being points, which is nothing but this list of points. Okay, so our angular step is pi by 2, which is expected because each of the points lies on one axis. So x axis, y axis, negative x axis, and negative y axis. So this is 5.625 is what I am saying. Suppose I change this to 8. There is an increase in uh, perimeter. Suppose I increase this to 16. There is a very small increase now. Suppose I increase this to say 100. There is a negligible change here. So what is happening? You can see that this value coming close to is very close to 2 pi. So why is this the case? Let us have a look at it through matplotlib by plotting a circle as well as this polygon side by side. Sorry, like into the same plot and see what happens. So we are defining our figure and axis. Then we are defining a center and radius for our circle, which is center is 0, 0, radius is 1. We create a circular patch by simply doing plt.circle with center radius. We tell it that the circle should not be filled and it should have a boundary of blue. This is how I'm doing it. Another way to do it is we could say take 1000 equidistant points on the circle and plot just x1, y1, x2, y2 all the way using plt.plot, which is, if you remember, plt.plot is nothing but a series of one after another series of straight line segments between two adjacent points xi, yi, and xi, yi plus n. So we add this code basically adds a circle with a center 0, 0, center at origin, unit radius, which is not filled and has a boundary of color blue. Next, in the same plot itself, we'll be adding a polygon. But before we do so, it's important to remember that our points function, equally spaced points on a circle, gives us a list of points which starts from the first point P1, P2, P3 all the way till Pn. However, it misses out this last remaining segment. So the way to deal with this is we add the first point, which was P1, again at the end of our points array. So I'll set my, say, the points value to 4. You can see that at the moment, or if I'm when I'm printing points, my points is P1, P2, P3, and P4. Once I do this and say I print points, we'll see what happens. But you can see that it is P1, P2, P3, P4, and again we go back to P1. What happens if we don't do this? I'll just comment this out and try printing. Oh, sorry. I have to go back here. This is my points again, P1, P2, P3, P4. You can see that the segment from P4 to P1 is missing. So um, a very small thing, but often like little things like this can miss our eye and then cause us problem later when running the code. Finally, I'm invoking plt.plot to plot all the points with my x array being the first entry for each of the points and the y array being the second entry for each of the points. I'm asking it to use color red and have a line width of 2 with circles at the end of the line segment. I will set my x-axis and y-axis limits to -1.5 and 1.5 and set the aspect ratio to be 1, and then I'm printing it. So you could find this ax.setlim, ylim, set aspect, as well as add patch, all those things once you explore the methods associated with explore all the methods which come in the matplotlib.pyplot module. So this is how my four-sided polygon looks like. Suppose I change it to say 5. What will happen then? Again, P1 is always on the x-axis, and then you have 5 equidistant points. If I change this to say 6, you expect it to be a hexagon because one vertex is on x-axis. If I change this to say 8, an octagon, you can see that now the distance between these 2 points, any two consecutive points, is much closer to the length of the arc as compared to, say, the case when we had, say, n equals 4. Here you can clearly see that the side length is much different from the arc length. But as our number of points increases, it rapidly becomes the same. So with 16 points starting to look like a circle itself, suppose I change this to say 40 points. Just comment this print of points. You can see that now it's much harder for you to distinguish which is your unit circle and which is your polygon. And here our perimeter turns out to be 6.27276 now. Say I do this to 100 and it's almost a circular bead. Okay, and you can also see that our value converges to 2 pi. Okay, so graphically this gives you an intuition that when we want to calculate, uh, suppose you want to calculate the circumference of a circle, you could do it by dividing it into n different points, n equidistant points lying on the circle itself, and then summing up the distance of those, summing up the side lengths for all the sides. That should give you the perimeter of this. That should approximate the perimeter of circle. for very large values, it will be almost the same. And the perimeter of a unit circle, perimeter of a circle as we know is nothing but 2 pi r. For a unit circle, r being 1, perimeter becomes 2 pi, which is also what our code is suggesting. If I increase this to say 1000, I don't think we'll be able to see anything at all now. Right. So this is another way for, we already looked through the Monte Carlo method how to approximate pi. Think of this as another way to approximate pi. Calculate the perimeter of a unit circle by using a regular polygon and just keep on increasing n. Divide that by 2 and you should get your pi. Okay. The next example that I have is, I hope this problem is clear. If not, you could raise your hands or just post it in the chat box. Okay. I believe that this is clear. The next example that we have is, I want to do an experiment. So one of the plots that professor had mentioned in Matplotlib is something called as a histogram plot. There are also other plots like pie chart and box plots. So I'm using this example to demonstrate what a histogram, how we can create a histogram plot and basically play with it a bit. So we have two random numbers between one. We are selecting two random numbers between 1 and 6 and summing them up. This is basically two random die numbered from 1 to 6 are being thrown, and whatever value comes up on the top face, we are just looking at it and summing them up. So you would have done this probably in Ludo or other board games where you have like multiple one or two die and just throwing them randomly and seeing what sort of number do we get. You expect the number to be between 2 and 12, 1 plus 1 and 6 plus 6, and we want to repeat this experiment a few times, and then we want to see how the sum is distributed, like how many times can we get 2, how many times we can get say 7, how many times we can expect to get 12. Note that this is a random experiment, so we do not know exactly how many times we'll get, but we can calculate an expectation or a mean number of times that we'll get that particular sum. So again, we begin by the same same approach, where we first import our important modules, which are random and matplotlib.pyplot. Then we assign a number of experiments, say like 1000 experiments, and then I'm creating a list which will store the sum of two dice rolls which occur at the end of each experiment. So for each of the 1000 experiments, we'll sum dice 1 plus dice 2 and store this in the list sums. And then I'm running this for loop. So I'm using here some for underscore in the range of number of experiments. This underscore is basically a placeholder for the iterator which is given in the for loop. So I could write say for I in the range of number of experiments, but there is nothing, I am doing nothing with the variable I itself. So unnecessarily some memory gets assigned to it. So I could just put an underscore instead, and range of number of experiments, range of 1000, so 0 to 999. Dice 1 is nothing but random.randint between 1 and 6, which is our first roll of our first die. Similarly, when we roll the second die, we randomly choose a number between 1 and 6. Our total for that particular experiment is just the sum of the two die, and that total at the end of each experiment is appended to our list, which is sums. It's important to be careful here to not write sum itself because sum is an inbuilt function in Python. So you can see that sum is an inbuilt function in Python. If say by mistake you were to write sum here and sum here, then now your sum will throw some error. It's saying that a built-in function has no attribute. Okay, and if I now check what my sum is, next we create a histogram plot. So there is a lot happening here. I'll go step by step. Firstly, we could look at if there are any confusion, we could simply use the help function plt dot. So that this will tell you, the help will tell you what inputs histogram takes. So it takes something x, bins, range, density, and so on, and explanation of each of this is given. So x is nothing but an array or a sequence of n arrays. Bins are basically the, say, the number of bins that we want to show. So bins are basically the number of bins that we want to show in our plot. So I'll do this step by step. First, I'll simply plot plt.hist for the array sums and then do plt.show. Let's see what happens. So it's automatically creating a histogram plot and it's doing some sort of sorting. It's not clear whether, say, this value belongs to 12 or this value belongs to 11, this histogram bar. Okay, so now we tell it to take bins from 2 to 4, sorry, 2 to 14. So it will start at 2, end at 13, and it seems that there is some sort of clarity now. All the histogram bins for each particular value seem to be starting. So like this is the bin for sum 2, this is the bin for sum 3, this is the bin for sum 4, sum 5, 6, 7, all the way to 12. But we still want to show this in a bit better light. So I'll just add this function called as align. Sorry, this argument called as align and ask it to align to left. So what this does is it pushes the histogram bar to the left of whatever value we have. So it was initially starting at 2, now it's moved to the left of 2. All these histograms are very close together, so we are using something called as relative width. Relative width will shrink the width of each of these bins. So currently the bin width is 1, we are specifying the bin width to become 0.75. And then we are adding X label, Y label, and title and showing the plot. So now with decrease in relative width, you can see that this is how our plot looks like. This is also, using these options are important, like the bins, align, relative width, because it makes our plot more easily interpretable, which means that whatever information we wish to convey through this plot can be transferred quickly. And suppose I were to change this experiment to a large value and then restart it. Let's remove this cell. You can see that it's sort of becoming smoother. Remove this cell also. If I increase it to a very large value, it's almost symmetric. So, which is what we expect provided that we have um, if you want to calculate, if you want to see like which sum is most likely, you can see that the sum of 7 is the most likely sum. This is because two dice can be summed up in 7 in the most number of ways: 1, 6, 2, 5, 3, 4, 4, 3, 5, 2, and 6, 1. So, like there are 6 different ways to obtain the sum 7. There are only 5 different ways to obtain the sum 6 and 8. There are 4 different ways to obtain the sums 5 and 9, and so on and so forth. There is exactly one way to obtain 12. So out of total 6 into 6, which is 36 possible combinations that we can get on two dice, uh, there is only one way to get 2, one way to get the sum 12. If I want to, right now you can see that this frequency is on the basis of total number of plots, but we could also scale this down to a percentage of the total number of experiments. That would also make it even more uh, acceptable. Okay, next we'll again look at matplotlib, but we'll use it to plot a few parametric functions in 2D. The first parametric function that we have here is ellipse. Okay, before we go here, I hope this histogram plot example is clear. If not, you could raise your hands and let me know.
Yes, sir.
Okay, thank you. The next example that we have is plotting a few parametric functions in 2D. So parametric functions are the form x of t and y of t, where t is like an independent variable which feeds, and from that we obtain say multiple uh, functions x and y. We are looking at one of the simplest parametric equations, which is an ellipse. So x is a cos t, y is b sine of t. You can see that if I do x by a whole square, which is cos square, and y by b whole square, which is sine square, so you essentially get x by a whole square plus y by b whole square equaling 1, which is nothing but equation of an ellipse whose major and minor axes are aligned with x and y axis of the Cartesian coordinate. A and b are constants which basically determine the length of major and minor axis. Okay, with this in mind, again, we start by importing our important libraries, which are matplotlib.pyplot and numpy. Here I have taken any two values for the major and minor axis. Then I'm taking t to be to vary from 0 to 2 pi, which is like the angular, which is the overall angle covered by one complete circle, and splitting that into 1,000 points. And we are writing our parametric equation as a cos 2 pi t and b sin 2 pi t. Sorry, a cos of t and b sin. Sorry, and then I'm creating creating a creating a figure in the xy plane which has equal width and height 6 6, plotting x comma y with the color blue, and I'm setting that my axis should be equal. If I run this script, you can see that this is the ellipse that I get. Where does this occur? So the most common example of this occurring is in the simple harmonic motion, wherein you can have something called as a phase plot. So, okay, so phase space plots in simple harmonic motion. So we know that for the simple harmonic motion, the displacement can be written as x of t being x of t is nothing but say a cos omega t plus phi, and my velocity v of t being a omega sine of omega t plus phi. If I have these equations as the displacement and velocity relations in simple harmonic motion, I can use this to plot the phase space plot, which basically looks like an ellipse. If I'm to copy this here, what I'll do is the simple harmonic motion. Suppose my amplitude is 1 and my frequency is 2, and my this is my amplitude, this is my angular frequency. I'll change this to 2 times n dot pi. So my angular frequency, this gives me my frequency as 1 hertz because omega is 2 pi, 2 pi into frequency. And suppose my phase is set to 0. So I have a very simple equation, and then I vary my time. So my frequency is 1 hertz, which means that my particle will move complete one cycle within 1 second. So I'll just say plot the particle for 2 cycles, plot the particle motion for 2 cycles, and then I'll plot what my parametric equations say: a cos omega t plus phi, a sin omega t plus phi. Sorry, a omega times omega t plus phi. So this becomes my velocity v. And if I want to plot x comma y now, okay, this is taking a bit of time. Okay, I have to x comma v. I made a mistake here. Sorry. So this is how my ellipse turns out to be. So this is basically my phase space plot for SHM. And if I play with around this, suppose I set my frequency to zero point 0.5 hertz, my phase space plot looks like this. Okay, and suppose I also want to see what my x comma t plots look like. Lt dot x comma t. This is my displacement in SHM. So you can see, oh, sorry, t comma x. I missed it. T comma x. If I look at my displacement, completes like one cycle within 2 seconds, which is what a frequency of 0.5 hertz mean. If I change this again to say frequency of 1 hertz and again plot it, I am seeing that my particle completes 2 cycles. Playing around with the phase value, suppose I give it a phase of say 1, the particle will start at some point in between, complete 2 cycles. And if I also plot the velocity response, can do away with this equal axis for for the SHM example. Right, so again my velocity is also a periodic function. Okay, so this is a practical example of where we use parametric plots. This is in the case of simple harmonic motion. There are other interesting parametric plots. Uh, okay, this is called as a hypotrochoid. So what this plot does is it basically tracks a particle which say lies on the edge of a circle and uh, tries to see what sort of motion the particle will go through. And the parametric equation for the same are x is equal to r minus r cos t and plus minus d times sine of r minus r by r t. If I plot this, you can see a hypertrophoid looks something like this. So, like within a circle, you have another smaller circle, and you're trying to see how one point on the circle. So, I have a bigger circle of radius r, I have a smaller circle of radius 1, and I'm trying to see how the point moves about inside, how one particular point moves about as the smaller circle rolls in the inside the perimeter of the another circle. Suppose I change this to 8. My inner circle should complete 8 cycles, which is what I'm seeing. Were I to change this to say 16. Okay, so it's also an interesting case. Now you can see that my hypertrophoid basically starts mimicking a circle as my outer radius becomes much larger than the radius of the inner circle. Okay, another curve that we have chosen here is the rose curve, whose equation is given by cos of nt, cos of t, and y of t is cos of nt, sine of t. So there is a slower period, sine of t, cos of t, multiplied by a quicker period, which is cos of nt. So n being nt being like n times faster than the outer circle. So suppose I set n equals 1. What do you expect? You expect cos square t and cos t sine t. So ends up being a circle again. If I change it to 2, I get 2 petals. So like this is my first horizontal petal, this is my second vertical petal. If I change this to say 4, getting a nice pattern here. Changing this to 6. Right, so what we have done in the code is again the same thing. You have the t parameter, which is the angular parameter, going from 0 to 2 pi, being divided into a large number of points, and you are writing x and y arrays directly by doing this np.cos n into t. So this directly gets you an array of the form cos of nt for all the values t, and you are multiplying that term wise to another array which contains cos of t itself. So this is term wise multiplication between two uh, numpy arrays, as we have seen in the class, and similarly you write y of t using cos of nt into sine of t. Again term wise multiplication. Plot this. Again we have chosen equal axis, and now we are showing this. There is another thing called as Lissajous curve. This is particularly useful in like signal processing studies, where you want to see like how two different periodic functions a and b uh, A and B being the corresponding angular frequencies, how they interact with each other when they uh, at at some when they have some phase difference. So this is generated often in an oscilloscope. Again, we begin by the same process. Import our libraries, create our array for the parameters 0 to 2 pi divided into 1000 points, and give values to a, small b, and delta. And then using np.sign function, because t is again an np array, we can do a into t plus delta. A is a constant, delta is also a constant. So we end up having, we end up getting a numpy array, which is of the form a sine small a t plus delta, and again we get a different numpy array b times sine of small b into t. We plot this with the values chosen, our Lissajous curve comes out to be something like this. If I play around with the values a bit, suppose I look at a simpler case where small a and small b are equal and there is no phase difference. What do you expect? We expect both x of t and y of t to be same, going from -1 to 1. So it's like a, so the two functions are basically the same when you get like only a straight line with passing through origin and which has a, which has slope equal to 1. If I say change the value of first function, you see that there is a change in the slope of your Lissajous curve. Its its slope has half, indicating that one of the functions is double of the second function. If I just do np.phi as my phase difference, so these two functions are opposite to each other in phase, and Lissajous curve just becomes this line with negative slope. I go back to this. Basically now has become a case where x of t is ahead of y of is ahead from y of t by a term pi by 2. So you basically have a sine t plus pi by 2, which is nothing but sine of t plus pi by 2 is nothing but cos of t. So we basically have x of t is cos of t and y of t is sine of t. So your Lissajous curve becomes a nice unit circle. Okay, so from what sort of form this Lissajous curve takes, you can infer what sort of functions x of t and y of t are. This is again an example of which finds a lot of applications. Next, I hope these parametric plots are clear. If there is any doubt, you may ask it now. Okay. I think it's clear. So the next example that we have is a code for root finding methods. So we want to demonstrate both the Newton-Raphson as well as something called as the bisection method. So what is the bisection method? Bisection method is a way to find root of a function within a given interval. So suppose you have an interval which is of the form a comma b. This is your bisection function, right? So if you have been given this interval, only then you can use a bisection function. In the Newton-Raphson method, our Newton-Raphson method is a root finding method which is non-bounded. Which is open interval based, which means it does not require you to give a closed interval. The way bisection method works is it will first check the value of function at a and it will check the value of function at b. from these two values, it will determine if a root of the function lies within this given interval. How do we know that? If if you calculate function at a and function at b, suppose the value of function at a is some positive number and value of function at b is some negative number, then you know for sure that at some point between a and b the function had to cross over, provided cross at the value 0, provided that your function is continuous. Right. So if your function is continuous, if you know that for sure, then your function went from a positive value to 0 to a negative value as it went from A to B. So it's imperative that we look at the signs of the function on A and B. If they are different, then we can say that a root lies between this given interval. If the root lies between this given interval, you take a point, you take the midpoint, which is a plus b by 2. Again, check whether a plus b by 2 has a sign which is same as a or same as b, and from that you discard the point. Suppose a plus b by 2 in our case turns out to have a negative sign, so then your new interval becomes a comma a plus b by 2, because a has a positive sign for the function and a plus b by 2 has a negative sign. So that basically ensures your guarantee that your function remains, your 0 remains within the interval. And this is how the bisection method works. It's a slow process, every time halving. Suppose you want to find the root of a function x square minus 1 and your interval is 0, 100. Then it will reduce to 0, 50, then it will reduce to 0, 25, then 0, 12.5, 0, 6.25, and so forth. So if used in some cases it will take a lot of time. So you want, this is uh, but this is a robust method in the sense that if your root lies in the given interval and you have provided you have given sufficient number of iterations, bisection method will find your root. That much is guaranteed. So it will definitely get to a solution. So all the logic that we just discussed is written in this function called as bisection method. It takes a function, it takes value a and b, which are the left and right ends of your interval. It has a tolerance set to 1e minus 6 and maximum iteration set to 100. First thing it does is checks if the function has positive and negative signs at the two ends. If both are positive or if both are negative, their product will be greater than 0, which means that we are telling it that the function has same sign. Our chosen interval a comma b may not be correct. It may be correct, but it may not be correct. So we no longer have the guarantee to converge to a solution. So we just return from that point. If if for the case where we do have that guarantee, fa into fb is less than 0, then what we do is we ask it to iterate up to our maximum iterations, calculate the midpoint of a comma b, check if the a comma b is tolerance of value of the function at c at the midpoint is less than our tolerance. If yes, return c. If not, we check whether the signs are opposite for the interval a comma c or they are opposite for the interval c comma b. Based on that, reassign a and b. If even after completing all our iterations we do not get anything, we just print out that it did not converge within our specified maximum iterations. So hopefully this is clear. I'll just run this function. Then we define an equation using we are defining our function as x square minus 4 and our function is func1 equaling lambda x square minus 4. So what exactly is happening here is, I'll go to the section at the end where we look at the lambda function. So in Python, we use lambda to create like a small anonymous function with like very simple where you do not have like a where you have like short simple operations that you can just write in the same line. An example of the same, and the syntax for that is you write lambda, you write the arguments involved, and you write the expression between those arguments. Suppose you want to define a function called a square which takes an input x and returns x square. So instead of writing the whole thing which is define square of x, return x square minus 4, sorry, x square, return x square, we just write it in a single line using the lambda function. So square is a function which takes input x and returns output x square. So if I just run this and print square of 4, I expect my output to be 16. Another example is that lambda can take multiple arguments. So suppose I create a new function called as add, which takes two arguments x comma y and returns output x plus y. Then my add becomes a small quick function. And, right, so lambda functions are particularly useful when we want to define like small throwaway functions, like where a full functional definition is not necessary. But if you have a complex function, so like the bisection method function, this is a very complex function. You cannot write this in a single line. So here we won't use lambda, but we'll use lambda when defining the function x square minus 4, whose root we are interested in finding. Okay, and then I'm asking it to calculate the root of function func1 using bisection method lying between the interval minus 3 and 1. So it gives the root as 2. Suppose I change my interval to be 1 comma 3. The root of x square minus 4 should be 2, which is what we are getting in this interval. Suppose I change this to minus 3 comma 3. Bisection, what happened here? We know that x square minus 4 has roots between minus 3 and 3. In fact, there are two roots between minus 3 and 3. But if we calculate the function value at minus 3 and plus 3, they are both equal to 5 plus 5. So our function, our bisection method no longer knows whether there is 0 root or 2 root or 4 roots or 6 roots and so on. Which is why this check is important. Another thing I could do is, suppose I want to find the roots between 0 and 100, where I specify my maximum iteration to be a small value. Suppose I only want to run for 3 iterations or 5 iterations. What happens here? You see that our method has not converged. This is because, sorry, this is because our bisection method will first go to 50, then 25, then 12.5, then 6.25, then 3.25. Whereas our root actually lies at a smaller value. So if I want to say give 10 iterations, even then the bisection method doesn't converge. If I want to give say 20 iterations, still no convergence. Oh, I wrote it here. Sorry, I wrote the wrong thing here. One second. I wanted to do this. This is a different function, exponential of this is my function. Right. So if I change my maximum iterations to say 10, my x square minus 2 is not solved. If I change my maximum iterations to 20, still my x square minus 4 is not solved. If I change it to say 30, now we have a solution. So somewhere between 20 and 30, say like 25, even after 25 iterations, it's not solved. So a simple function like So bisection method, while robust, is slow. A different function that we are looking at here is func2 defined as e raised to x minus 2, and for that we want to find for a solution x. So, or suppose I do np dot, right. So I again invoke the bisection method and ask it to find root between 0 and 2. It will take some iterations and print it out. Okay. So e raised to x minus 2, we have obtained the solution to be the other method that we look for finding a root was the Newton-Raphson method, which is an iterative method. It uses an initial guess, creates a tangent line from the initial guess to the curve, and then from that tangent line estimates where the next guess, where the root is. So it gets a next guess, and it keeps on doing this. This works especially when, well, if the initial guess is close to the root, but it may not if the initial guess is far. Again, I think the code for this has been shown in the class itself, but I'll just show it here. So you have a function, you have f of x, df by dx, my initial guess, tolerance, maximum iterations, and for each of the for each iteration, I'm just adding x minus function of x minus f of x upon f dash of x as my new guess using this line, and then checking if my absolute value is within convergence, within tolerance, sorry. If not, I'm printing that it did not converge. So suppose I use this to solve for my function x square minus 4 equal to 0. My derivative of x, f of x is 2x, and I use this to solve my Newton-Raphson method. And I know that the root should be 2 or minus 2. Suppose I give the value 1.7 and ask it to calculate what happens. It gives the value 2. Suppose I give it a value of 3, still converges. Suppose I give it a value minus 0.01, again converges to a value, right? Same exercise is repeated for a different function, e raised to x minus 2, whose derivative is nothing but e raised to x. Now if I run this function, again I get the value root s, x is equal to 0.6931. Were I to say start at a different point, still get this value. So this also depends on the nature of this function that we are doing. This is e raised to x minus 2, so it's a monotonous function, monotonous increasing function. So Newton-Raphson method is good at like quickly find the roots in such a case. However, if you have say like an oscillatory function where things are going up and down, then this might get stuck in between. So it doesn't guarantee you convergence in the same way bisection can guarantee you, provided you give the correct interval. Okay, these root finding methods are particularly important uh, when you will be dealing with, sorry, numerical, when you will be doing say a course like numerical methods in engineering. In such a course you will learn to solve this using other method, root finding using other methods, including say the second method. It's also popular. Okay, so I hope both the bisection and Newton-Raphson methods, the logic behind them, and the codes associated are clear. If not, you may stop me now. Okay. something. Okay. Next thing we want to do is to create a algebraic system with random inputs a and x equaling b, and we want to see if it's solvable. So again, we start with numpy, and by importing numpy, we randomly choose a number between 2 and 6, 2 and 5, which basically gives us the size of our matrix A, and then we create a random matrix with 0 and 1 as input. So, sorry, with whose inputs are between randomly chosen between 0 and 1. If I run this, suppose I run this again. So the size of A is not fixed, as well as the inputs of A are not fixed. Only thing that is fixed is that A is a square matrix. We want to check if A is non-singular. So if I run this while loop, most of the times you'll see that almost all the A that we can generate are non-singular. Only in very few cases your where your columns are dependent on each other, only then A will become singular. Then we again randomly generate a vector B, just say, and this is my B vector, and now we want to solve for Ax equal to B. So the essential condition is that the matrix A should be square and A should be full rank, or its determinant is non-zero. Only then this system is solvable, and we solve it using NP linear algebra model NumPy in NumPy, and NP linear solve A B. This will create the vector. This will find the vector A which satisfies our solution. So if I want to do this is a matrix A B, and solution A into X should equal to B, and I am also printing the determinant of matrix A. Okay. Okay. The final example that I have for today's session is a code which will calculate volume of common three-dimensional objects. So the way that I have chosen to do so is I start off by importing the math module. Then I write different one-line functions for different common 3D solids. Say a cube, a rectangular prism, a sphere, or cylinder, or a cone. Right? For the cube, we know that volume is nothing but A cube. It's a side length cube. For prism, it is L into B into H. For sphere, it's 4 by 3 pi r cube. For cylinder, it's pi r square H. And for a cone, it's 1/3 pi r square H. So a series of very small functions I have written. And now I create the user interactive part. So user input part. So I'm printing a statement I'm printing a series of statements one after the other, which ask the user, which tell the user which number is associated with which choice, and then asks him to input the number of his choice. Suppose I run this, I'm interested in a cube, I'll enter the number 1. Next, I have a series of if-else choices, big series of if-else choices. This can also be done using something called as case. You can look that up yourself also. So, like if you have the same variable whose value you want to check across say a list of possible options that variable can take up, you can use something called as case. So I'm doing this. I have created a list of, sorry, a series of conditionals one after other, and I'm just saying that if the choice is one, which means it's a cube, then I only need the input called a side length. I ask the user to input the length of the side of cube, calculate volume of the cube as using my volume cube function with input as side length. Just print the volume of the cube. Suppose my choice is 2, which is a rectangular prism. I ask the user to first enter the length, then the width, and then the height of my rectangular prism. Use this three to calculate the total volume of this rectangular prism and output that. If I want to say calculate the volume of a sphere, only the radius is needed, which is what I ask the user. Invoke my volume sphere function to print my output. If my choice is say a cylinder, I need two inputs, the radius and height of the cylinder. Invoke my volume cylinder function and print the volume of the cylinder. If my choice is 5, which is my cone requires a radius and a height. So I write cylindrical, sorry, sorry, right cone, and we calculate the volume of the cone using volume cone function and print it. If my choice violates any of these integers, I just print that you have entered a wrong option. So we'll start again. I'll from my functions get, suppose I enter the choice say -1. There is no choice -1, and if I run this function now, it will tell me that I have selected a wrong option. If I again go back to this choice, run a cube with a side of, suppose side length of 2, then I expect my volume to be 2 cube, which is exactly what we are getting from our function. If I wanted to say choose a prism, rectangular prism with length 10, height width 3, height 4, I expect the volume to be 120, which is nothing but L into V into H. If I have a sphere, we only have the radius. Suppose 3 is my radius, then 4 by 3 pi r cube is nothing but 36 pi, which should be around 130. Yeah. Similarly, if I'm interested in the cylinder, again I run through this, radius of 2, height of suppose 10, I get some volume for it, pi r square h. And finally, if I want to look at cone will again require a radius. Suppose a radius of 3 and a height also of 3. So I get a volume of cone corresponding to that. Okay, so I think this completes the series of example problems that I had. I tried to address some of the pending issues or concepts that were mentioned in the class, including the args, keyword args, how to import a module from a different directory, then how do we calculate the perimeter of a, how we can use a uh, how we can use a polygon with like equal sides to try and estimate, which is inscribed in a unit circle to try and estimate our the value of pi. Then the histogram plot, which was again mentioned in the class. How do we do that? What are some of the options included with it? We also looked at the help function. Like at any point, if you have a problem with one of these functions, you can just invoke help, which is inbuilt in Python. a few parametric functions and their applications, specifically like ellipse and how does an ellipse tally well with uh, the phase space plots in simple harmonic motion, and other examples including the hypotochride, which traces how a smaller circle or a disk with smaller radius moves inside a disk with a larger radius, the Rose curve, Lysage's curve, which tells us about how two signals are related, how are they same or different. We also looked at root finding method, specifically bisection method we looked at. Newton-Raphson was taught in class, but as a comparison, it was nice. And then how do we solve linear algebraic equation, which is particularly important for engineers. So as well as if any of you are interested later on in data science and all. We also looked at a simple choice function to calculate volume of common 3D solids. And finally, we looked at lambda somewhere in between itself, which was also introduced in the previous week's lectures, but uh, like the basics weren't like demonstrated clearly. Okay, so that covers what I had for this particular class. If you have any doubts, you can ask them apart from this, including any of the week 1, week 2 lectures that have been taken so far. Okay, I think if there are no more doubts, then I guess we can conclude today's session. Thank you for attending, and I hope to see you again in the next class. If any of you hasn't registered it, you could register for the examination at the end of this course. That will also get you a certificate, which might be important later on when you want to say look for a job which utilizes these particular skills. Hope you learned something new. And
Okay.
once again,
Okay,
thank
sir.
you.
Thank you.
Thank you.